right, welcome everyone. My name is Ryan Arnold. I'm the Linaro Toolchain Working Group Engineering Manager. I haven't been an engineering manager all my life, just the last few years. Before that, I've been involved in GNU Linux open source software enablement my whole career. So I'm going to talk about the lifecycle of the GNU Toolchain. So I want to start by casting you all in the role of the villain. So let's say your company has enabled a new microarchitecture variant of the ARM architecture. You want your customers to be able to use this and use your hardware as soon as the software is available and the hardware hits the market. So your team's been working on proprietary operating systems and compilers their whole career, and now they want to work in the open source communities. So they've worked very hard internally to enable the Linux kernel and the GNU Toolchain for your hardware. And now you finally have legal permission to gift this code to the GNU Linux OS projects. So you're on a tight schedule and you need your code to go to the distro as soon as possible so that your software, the software makes it to market when your hardware makes it there. So considering you want to get this code upstream, you think maybe these projects should stall their planned code freeze and give us time to get this code upstream, right? I mean, that seems reasonable. And maybe they should maintain the architecture code after our engineers have moved on to the next project and the next microarch variant. That seems reasonable, right? Well, unfortunately, that's not right, and this is the sort of attitude that a lot of companies take toward open source contribution. So there's a big problem with this method, and it's the form that the generosity takes. Did it switch? It did, okay. So I've been involved in open source enablement for the last 16 years. I worked on 10 microprocessor variants over that time as both a Linux kernel hacker in the early part of my career and as a GNU Toolchain engineer most recently. So I was formerly the glibc PowerPC maintainer and currently still a steward of the glibc community. I was also the maintainer of a number of secondary toolchain packages and worked closely with the Linux distribution vendors as business partners to get my company's code into distro products. So that's a little bit of background about me, which has informed this presentation. So I just wanted to let you guys know I actually do have some qualifications. So this isn't just me spouting information at you. So I've seen this gifting behavior in quite a few times throughout my career, and in fact, I've even been guilty of some of it at times. So I want to address this in the context of the toolchain lifecycle. So I have a parable. So one day I signed up for a raffle to win a huge dream house. This one, maybe. It even has a nice red bike shed. You see the bike shed in the back? Right there? So the builder wants to use the winner in an upcoming promotional event. So the winner would be required to take possession immediately. But if I won the house, I'd get a sour surprise when I received the property tax bill later that year. Could I even pay the property taxes without taking out on an extra job or shifting my financial priorities? What if things start to go wrong with the house? If this gift house has major structural flaws, it could take a massive amount of time and money to fix, and the burden would be on me. So this gift house could be a huge liability that could jeopardize my future plans. So this is a favorite quote of mine. I'm a home improvement guy. I've restored houses before, and this really kind of demonstrates how you are burdened by a house. If a man builds a fine house, and now he has a master and a task for life. He is to furnish, watch, show it, and keep it in repair the rest of his days. So this is an Emerson quote. So notice how this quote doesn't mention getting someone else to keep the house in good repair. So software bit rots just like a real house. It has maintenance costs. Oops, sorry. The more dependencies that software has, the faster it bit rots. And toolchains have a lot of dependencies. A toolchain, for instance, the GNU Toolchain is, I believe, around 5 or 6 core projects, all tied together, all intimately tied together. So an open source community is reluctant to accept gifts that are prone to bit rot, and many companies have tried to get open source communities to maintain their software. We call this abandonware. Some people have even demanded fixes from open source communities after the fact, such as, stop your code freeze, fix my bug. So back to you being the villain. So what you're trying to give these communities is likely at odds with their day job, and in fact, maybe in direct competition to it. So despite this, the maintainers understand that as many, we are strong. So they're willing and ready to work with you to build a house that they can afford to maintain. So source code gifts are often a large burden on the communities before they become a benefit. And as participants and benefactors, we have to be sensitive to the customs and schedules of each of these components of the software stack. So I wanted to start with this because you need to understand why open source engineers push back when someone tries to give them a gift house, because it's a loaded gun. There's more to it than just a gift. So before we look at the schedule that I talked about, I want to address one more major concern. So your goal is to get this enabled OS code in the hands of your customers because you want to get it on your hardware. And once it's gifted in the upstream, it can be deployed in the customer's hands, right? Like right into the data center? No. You actually need to get that code in a Linux distribution. So your customers don't have the skills or the desire to build their own tool chains or distributions. So an SoC vendor debuting a processor with no Linux support would have very limited industry adoption. So what do I mean by distro? A distro is a formally supported collection of interoperable programs. These programs have been quality and integration tested in order to guarantee they're compatible. So your code needs to be accepted into a Linux distro to get into your customer's hands. This ship represents a Linux distro. I use the ship as a representation because it took a long time to build, a long time to load. Once it leaves port, it'll be at sea a long time with no way to change its manifest. A distro company makes a commitment to support an OS release for years, so this ship is at sea for years. Maintaining a distro and supporting it is expensive, so the longer support is required, the more expensive it becomes. And because you have to maintain currency of knowledge and older infrastructure, the longer you support it, like I said, the more expensive it is. So back to the ship analogy. Ask the harbor master when the next ship will sail, and the answer might be years. So your code needs to be on that ship before it sails. And by that I mean your code needs to go upstream well before the Linux distro ships. So to add further complication, each distro has a different type of release. So is the distro going to take architecture enablement with every release? No, they're not. So here's an example of Canonical's Ubuntu release schedule. And these are the LTS releases, and these are their standard releases. So it's expressly written in Canonical's description of LTS that this is not a feature-based release. It only hardens existing functionality. It doesn't add functionality. So the orange bar is the next LTS release, which is an active maintenance, and that's every 2 years. So you need to get your fixes into these guys here, these gray releases. So this further tightens your upstreaming schedule. So I would roughly estimate your code needs to be upstream right about here. But don't quote me on that. I mean, this is probably actually even too late in some instances. I would like to point out that the distro does retain the right to prioritize their projects, in which case they might add your feature later in an LTS release, but I wouldn't count on it. So here's similar information for RHEL. They didn't have a nice graph on their webpage. Notice there's no RHEL 8 on there. They don't publish their projections for their RHEL 8 schedule at this point, as far as I know. But last I knew, they likewise encourage new feature adoption into their Fedora releases before adoption in their enterprise release. All right. So, excuse me? Roughly every 3 years, okay. So I led with the gift house and the ship because the major issue is how do you get the ship with the gift house on the ship before it sails? So you might ask, can't the distro just take my code without upstreaming it first? If you look back in LKML far enough, probably somewhere around 2004, you'll see me being flamed by Greg KH for asking or attempting to do exactly that. It wasn't pretty, and it was kind of embarrassing, but I thought I'd point it out because it's happened to me. So for the Linux OS distribution company, the risk of taking unvetted code, that is, unvetted code is that a related bug will incur significant costs later. So code taken in the distro but not upstream is the responsibility of the Linux distro to support. So point being, if you convince Red Hat to take a patch that's not upstream, and the customers go to the Linux community is going to kick it right back at Red Hat and say, your choice, your problem. So unvetted code is more likely to break in production, and this can have really expensive repercussions in these LTS releases. And the distros have been burned many times, and they're now quite strict about making it upstream first, the code, before they'll accept it. So sometimes they'll make an exception that's in their own business interests, but it'll be hard to convince them that your microarchitecture is one of those. One exception that you guys will be aware of is RHEL 7.2 did in fact ship ARM V8 AR64 support, whereas RHEL 7 originally did not have support. So believe, adopt, and embrace the open source mantra. Roughly, submit early, submit often. Get your code upstream, iterate on patch review, and resubmit often. So now I want to move on to where we discuss toolchain upstreaming. And I'm going to focus on ARM architecture licensees because the challenges are a subset of full architecture upstreaming, but probably most relevant to most of you here. Matt and all you guys at ARM are very familiar with the larger challenges, but like I said, I want to focus on the subset that's relevant to our licensees, or to ARM's licensees. So the order of upstreaming is different for a microarchitecture variant than for the new ISA. They can have code upstreamed in stages, whereas for a new ISA, enablement often has to go in large chunks. But I'm getting ahead of myself a bit. A new processor is a useless piece of silicon until the Linux kernel hackers and the toolchain engineers create a software port of the base OS to run on the hardware. And enablement of that processor follows a life cycle from the conception of the idea through the availability in the distro. So what is that life cycle? Well, it's all the steps of that process. So I literally mean from conception to the creation of the ISA all the way through adoption. And full Linux distribution adoption means including all the features of your hardware where the software can realize all the performance benefits of your hardware. As licensees, you are fortunate that should you just ship a product which conforms to the ISA, the reference platform will in fact work on your hardware. It will not be optimized. So it won't be running, you want full support, so you won't be running bare bones reference platform software. So you have to have a toolchain to build the software that runs on the system, and the toolchain is the first corner piece of a puzzle. So from the position of the software maintainers, the upstreaming process should start as soon as conceivably possible. ARM licensees are fortunate in that ARM and Linaro engineers have done substantial work to make sure that the ARM reference platform is available in the upstream packages. So here's a linear arc of the toolchain lifecycle. It includes more than the toolchain because the toolchain has to run on hardware and has to communicate with the kernel. I'm not going to go through these right now. We'll hit these later. But right around here, you'll see GNU Toolchain implementation. The whole GNU Linux operating system is a collection of projects that are loosely committed to interworking together if configured correctly. So you might think that project maintainers would work closely together to sync their schedules, right? Unfortunately, that's wrong. In fact, companies like ARM, Linaro, and Red Hat, and others have engineering teams that try to coordinate the package interoperability. So an ARM kernel engineer might talk to a Linaro compiler engineer, and then the Linaro compiler engineer talks to the glibc maintainer in Linaro to make sure that a certain feature hits upstream as soon as possible. But by design, each of these projects is schedule independent, and in fact, each project's engineers are easily annoyed if they feel that anyone else is trying to exert schedule pressure on them on behalf of some other interest. Because often this will undermine every other participant's own business objectives. So if you try to delay a release freeze for your own business interests, you're in fact possibly jeopardizing another company's schedule. So if you don't respect your competitors' schedules in this regard, they're not going to respect yours. So every community is an opportunity to bike shed, hence the red bike shed on the house. So accept that this will happen and be on the ground early enough that it doesn't cause catastrophic delay. So I keep saying early, 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 and what you need to keep thinking is earlier, earlier, earlier. So upstreaming might be delayed over what you perceive to be trivialities. So maybe the reality is more like this. You know, this big nasty cloud of stuff that happens, and if you're lucky, something comes out of it. But this isn't quite true. There's actually some order to the chaos, and that's what we're going to cover. But I want to start with another parable. So I had this dog. This isn't him, but I like bulldogs. Because I was taking a walk and saw a lady trying to drag a bulldog along the sidewalk. But likewise, my dog, I have a dog, and since I work at home, he doesn't get a lot of exercise, and sometimes if I take him on a walk or a run, when he's done running, he sits down and he won't move, and open source communities are like my dog. You're not going to get them to move. Some people will use their reputation and use their personal connections to try to pressure the community into doing what they want. But like my dog, he'll go home and he'll tear the stuffing out of the chair cushions in retaliation. You might find that once you've exhausted your company's goodwill, you're met with a hostile reaction in open source communities. Have you ever seen an email saying, "Go away"? I mean, that's exactly it. That's the dog sitting down. So it takes appropriate timing, knowing the schedule and dependencies, which we'll go over, and a correct social approach to get things done. So from your perspective, sufficient lead time is the most important factor. From the maintainer's perspective, early access to information and responsive refactoring to the patches is the most important factor. So why do maintainers need early access to information? So another parable. Where I live, I'm required to have a building permit for any modifications to a physical structure. My city requires a description of the work to be done before they'll grant the building permit, and it's to ensure the building is safe for future occupants, hence the rotting house. So I'm pretty skilled with a pair of linesman's pliers and wire strippers. I've added circuits to my breaker panel without electrocuting myself or burning my house down. Despite this, the city electrical inspector might take issue with what I intend to do. And he actually often enforces his own personal preferences that are not in the building code. They will require that the wiring that doesn't meet building code requirements be stripped out. This is directly applicable to open source software. Maintainers have preferences. Maintainers will require you tear out code that they don't like, and you can't do anything about it. I cannot get the building permit or the building inspector to do what I want. All right, so it's a very common practice for engineering teams to attempt to dump what they consider to be a completed feature onto an open source community without regard or consideration for who is to maintain this code in the future. And in this capacity, an open source maintainer will act like the building code inspector. So building a house is not a process where you simply show up on site, put up some walls on the bare dirt. It starts with talking to the necessary officials to get the legal approval to build a valid structure. So similarly, the lifecycle of GNU Toolchain is not a single moment in history where all the code's just dropped at once. It starts with talking to the necessary and correct people. So upstreaming is not a moment in time, but rather a collection of moments that should start as early as possible. When we think about the lifecycle of GNU Toolchain, we need to consider all the moments where the rain can get in and rot the house. So these are the points where the toolchain community should be involved early. The following phases roughly represent the major moments in the lifecycle, grouped by similarity of purpose. So we have legal branding, platform enablement, ABI enablement, optimization, and distro adoption. You could argue with me that there are many steps in between and around, and you'd probably be right, but I wanted to keep it brief. So we'll start with legal and branding. Most companies that have new intellectual property require legal approval before engineers can start open sourcing. But like I said, open sourcing is not a single moment. It's a process of feedback and resubmission, which will finally culminate in upstream acceptance of code. And I keep saying you need to get code in as soon as possible, but you also need to get approval as soon as possible. But I'm not talking about approval to upstream a large patch set. I'm talking about getting approval to work upstream. And your legal departments need to trust that you will do the right thing so you can start the process early so that the very first patch can go upstream as early as possible. So if your legal department is dragging their feet on approving upstream contribution, your schedule is in jeopardy. I've seen many companies held up with this, with a full set of enablement patches waiting for legal approval, all hinging on a tight schedule, and not realizing that there's still a lot of work to do. So the other part is branding. But not really. So company branding is not the same as open source naming, and these topics are often conflated. The problem is when one of you as an engineer pushes code upstream that says this is, chip foo, and your marketing department comes back and says, no, it's chip bar, and you've already submitted patches, and then they come back later and say, well, it's chip zap, and they keep changing things on you. The reality is, don't get stuck equating the brand with the chip name. And in fact, the open source community might have a say in what they want to call your chip. They might not like what you want to call your chip. And depending on your position in the community, they might not let you have a chance to call your chip what you want to call it in the open source packages. And in reality, it really doesn't matter. So phase 0 is boring, but if you don't get the right approval to build a house, you might build too close to the property line, for instance, which is illegal. So let's move on to phase 1, platform enablement. So this describes the first stage of development in most projects, where the platform is identified to the project and a minimum set of work is done. And the first requirement for enablement is the ISA. So if you have an ISA, I would say release it as soon as you can. If you keep it internal, you'd better be prepared to do all the work. You will be held to a higher standard. So this tactic should be reserved for those companies that already have a good reputation in the communities and have a reserve of trust. So once the open source maintainers have actually been known to block upstream acceptance of a port because of the lack of ability of an ISA. They'll basically say, hey, as soon as you publish the docs, I'll take your patch. So if we relate this whole thing back to the gift house metaphor, this is akin to wanting to know what sort of ground the house is built on and what's inside of the walls before agreeing to maintain the house. So one thing you don't want to do is ask the community for help but refuse to provide the ISA. This is like saying, you know, yeah, that's exactly it. Help me, help me, help me, but I can't tell you what I need help with. And this is actually pretty common. So ARM licensees are fortunate that the ARM instruction set architecture is mostly publicly available at this point. So a secondary element that helps with platform enablement is the availability of software models. This is something that ARM very much did right with the foundation model early. Okay, so I want to talk, you're going to see some of these stop signs, you're going to see some danger things, and you're going to see some pro tips. You've seen pro tips already. So it's a cardinal sin to implement a microarchitecture and leave out the non-optional parts of the ISA. So don't leave out SIMD. Don't leave out hard float in ARM v8, 64-bit. It's just an absolute nightmare for you. So the entire OS software stack assumes the availability of Neon and floating point, and the proper functioning of that software stack relies on it. So leaving it out means entire code paths will be filled with illegal operations. All right, so we talked about models. So a model is an emulation environment that simulates the hardware as defined by the ISA. So open source communities are often not interested in signing NDAs. So there's no access to the hardware for open source engineers unless you make these models available to them outside of NDA. So this is a good reason to leverage your relationship with Linaro and ARM, as we have a strong open source presence, and in the early days with Foundation model, we could work on enablement on member behalf in that way. So a successful company will explore the options for the ISA and ABIs years before the schedule pressure forces any public announcement. They make the distribution distribution of the model widely available as possible, including to key community members. On the other hand, a company that provides no model or execution engine will struggle to prove to the communities that their port is actually functional. So we have the ISA and we have models. What's next? Well, there's a number of activities that can kick off at the same time, and these are kernel enablement, compiler, assembler, linker, and system platform identification. So much has been written about getting code upstream into the Linux kernel, so I won't go into detail. But we'll touch on some points that relate directly to the toolchain. Linux kernel platform enablement code is the code that allows the kernel to detect the microarchitecture, boot the machine, and export the necessary information to the user space via the communication contract, which is called the KABI. So this is the contract between kernel and user space applications about what the kernel expects and returns regarding structures, syscall interfaces, register vulnerability, feature enablement, register access, etc. So it's important to understand that while the compiler, linker, and assembler platform enablement code can go upstream in parallel with the Linux kernel, the C library must wait until the KABI is committed upstream before accepting patches. So this means that glibc won't accept code until the kernel has baked the KABI code. And this is a hard dependency. And it's because we never want a version of glibc released in the wild that identifies a platform before the kernel recognizes it. And this is to prevent incompatible application code incompatible applications with incompatible kernel ABIs from being released in the wild. And this is all a maintenance issue. Distros don't want to maintain it. Different versions that don't support each other, and the communities don't want to maintain it either. It's impossible to hunt bugs. So in general, the Linux kernel releases a new release every 2 years. There is a Linux long-term kernel, and these have the Linux releases are every 2 to 3 months. Long-term kernels have a longer supported lifespan. If you look at this, I don't know why some of these are going to be maintained for 5 years and some for 3 and some for 2. So distro kernels don't have to track these, but it's possible they're tracked relatively closely. But my assumption is they have their own long-term kernels. So I believe if you look at RHEL 7, it's based on kernel 310 and will be for the rest of its life. So if a distro ships a kernel that doesn't have support for your microarchitecture variant, your system libraries won't be able to detect the platform. And it's likely the distro won't even boot your board. So the point is, you need upstream Linux kernel support, or the rest of the work in the other projects is pointless. So like I said, RHEL 7 is still on a 310 kernel with significant patching. So what kernel will RHEL 8 use? It's a good bet it'll be something in Fedora first. So the first patches to hit the toolchain are microarchitecture identification. So from a trustworthy SoC vendor, and your reputation precedes you, by the way, the GNU Toolchain community will accept an architecture identification patch to the assembler, linker, and compiler before full enablement. If you're new, they might not. They might not trust that you're going to stick around or that your hardware will even hit market. So at a minimum, this code allows the linker, assembler, and compiler to know what kind of code they're generating and for what platform. And this work can proceed in tandem with kernel development. For a microarchitecture variant, these first patches may simply clone the behavior of the reference platform and assign the name of the microarchitecture variant. So following this, we have the instruction set specific changes. And these are pipeline descriptions and microarchitecture variants of the cost model, and these can go upstream. At this point, the code is often first passed and based on the best guess performance characteristics. In later stages, these are tuned with heuristics once real hardware is actually available. So here's the danger. Sometimes early enablement might give away the details of the processor, such as information about the pipeline bandwidth. If this is sensitive, what you need to do is make sure that the pipeline description that you export or announce is the same as the reference platform until such time as you've actually announced the hardware. So just be aware of that, sometimes the code that you upstream can give away details. But you can upstream that code in parts later. So this is the GCC development release schedule. The important thing to take note of here is stage 1. So we have stage 1 here, and we have stage 1 here. So we're in GCC 7 stage 1 right now. Stage 1 is the gatekeeper to the release. It's a 6-month window where the tree is open for new features and invasive fixes. Once stage 1 closes, no new features will be allowed for another 6 months while the next release is stabilizing. So the implication here is that if you miss GCC stage 1, your enablement patches will have to wait a minimum of 1.5 years for the next release to actually hit a distro, to have a chance of hitting a distro. So you need to make sure you get those patches into stage 1. So if you're ever in a status, you're watching a status update where I'm talking about stage 1, it's why compiler engineers and those of us that release compiler software are obsessed with stage 1, hitting stage 1. We don't want to wait 1.5 years. The first step for glibc is to enable the code which will expressly build glibc for the target microarchitecture variant. So this means that you need a compiler that can build the new variant, at least nominally, and you also need glibc to build the framework changes in order to recognize you're building for that new architecture. At first, the new microarchitecture variant will, in fact, adopt the reference platform, and this is okay. You can submit these patches in little pieces that basically say, oh yeah, I'm just like A57, and then come back later and say, well, I'm a little different than A57, and that's perfectly acceptable. So if you look at the glibc release schedule, this is about every 6 months. So there's a month-long freeze before the release, and the window for every new code is open for about 2 5-month periods a year. So how do we know what versions of glibc will make Ubuntu or RHEL distro releases? So it's a safe bet that they'll pick up the glibc version from the latest non-LTS release or from Fedora, as we said before. But it's not unheard of for the distro to pick up the latest version of glibc that they can. This is because glibc's ability to identify the target is pivotal to the distro being able to execute platform-specific code. And we'll get a little bit more into that in a little bit. So here's another pro tip. Get that KABI enablement code upstream as soon as possible. Only after that code is baked can glibc platform identify what hardware you're on. And this is a hard requirement. glibc implements the user space side of the KBI contract. So after the platform identification, you need glibc to be able to, 1, implement the syscall interface, 2, detect and query the microarchitecture information in the kernel platform information that via the aux vector, and 3, implement the ifunc mechanism for the architecture. So if there's anything controversial in the new KABI, the glibc community will block upstream acceptance of your patches on acceptance of the KABI. So you might have everything ready to go and still miss your target glibc date. So the reason this is important is that if a Linux distro can identify the hardware it's running on, it can add that support to the distro. And in some circumstances, the optimizations might be added later. I'm not promising I don't work for the distro. Don't quote me on it, but it's happened in the past. But in reality, your code for glibc won't be accepted upstream until any necessary ABI changes have been implemented as well, which is part of the next phase. And before I get there, I hope you don't need ABI changes. So let's sidetrack very quickly to talk about Rev 1 hardware. So if you're lucky, you'll get the hardware on schedule before you start working on ABI enablement. And this will show that your early assumptions on the ABI can in fact actually be realized in hardware. Unfortunately, of the 10 architecture enablements I've been involved in, none of them have been on time. So accept the reality. The necessary chain of events can't be based upon an assumption that everything is going to go according to the schedule, particularly the hardware release schedule. So Rev 1 hardware means that the compiler cost model tables can be updated based on execution data. All right, back to ABIs. So the ABI is the application binary interface, and it's the contract between applications about how the binary is laid out in memory and how it interacts with other applications. So for instance, the dynamic linker and how the dynamic linker interacts with applications that it loads and executes. So hopefully for microarchitecture variants, this is minimal or non-existent, though it's possible that a new microarchitecture variant will debut a new ISA feature first, and thus we'll have to implement an ABI change or addition. You will be forced to separate those. One will have to go in against the reference platform. The ISA will apply to all microarchitecture variants that are covered by the ISA, and then your secondary patch will be able to implement your new features. So even in this case, ARM will often enable the new ISA additions into the reference platform on your behalf before microarchitecture enablement is necessary. Okay, so using an existing API. So a microarchitecture variant is able to inherit from the code base of the parent architecture and should generally not need a new ABI. And almost every architecture variant will have an opportunity where they think to themselves, you know, it'd be a lot easier and cheaper on us if we just created our own ABI or broke the existing one. Just don't do it. The fastest path to upstreaming is to use the existing ABI. So if you implemented all the required parts of the ISA, if you've not implemented all the parts of the ISA, you've actually defined a new ABI. So remember when I was talking about releasing software that doesn't have neon or releasing hardware that doesn't have neon and doesn't have hard float? You have a new ABI. You have to re-implement all of the code which assumed neon and assumed a floating point unit. This is a mountain of work. So the pro tip is don't use an ABI change as a way to squeeze out more performance. unless it's a benefit to all microarchitecture variants. So if you're trying to squeeze out performance, proposing an ABI change isn't the way to do it. You will be blocked by the community and the other parties that use the same ABI. All right, here's another danger. Nothing says lazy like a new ABI, or an ABI that significantly deviates from the established standards for no particular reason. Just don't do it. Maintainers will always try to push you toward an existing ABI. If you must have an ABI change, you absolutely must petition the invested parties as soon as possible. So once again, your lead time goes even further out. So an unsuccessful company will assume that they have the authority to make an ABI change where others have an invested interest, which will lead to blocking and stalling, and this can be deadly to your schedule. It also damages your reputation and will cause distrust in the future. All right, so here's another one of those cardinal sins. So it's a cardinal sin to release binaries compiled with a pre-release ABI into the wild. So this is a classic blunder. Why is this a sin? So if you've shipped code on a non-upstream ABI and there are bugs, customers will start asking someone to fix that, and who do you think they go to? They go to the open source community. And the open source community says, what's this? And you'll say, well, it's the code that runs on my architecture. And they'll say, well, this doesn't look like the code that went in upstream. And pretty soon you have this circle of blame where then they say, well, who permitted this code to be written this way? This isn't what we ship, and this isn't what the Linux distribution ships. So binary incompatibility between implementations is a real problem. Vendors of large software projects, they like the ability to forward port their software and their existing applications into new Linux distros. And then if the ABIs differ, this is impossible and a source of bizarre and difficult bugs. So think like large enterprise software suites. They don't want to have to recompile all that code just to run it on a new distro. And the distros do the best they can in order to allow backward compatibility. So just because you propose the ABI change doesn't mean you get to own the ABI. So you might not own the ABI even if you're the first person to define it. You might have to defer to those who own the predecessor ABI. All right, so moving on to GCC linker and assembler ABI changes. So if the ABI changes are required, they must first be implemented in the compiler and linker in tandem, and otherwise you can't generate code for the libraries to implement.